Okay, good morning everyone. So welcome to our seminar, and sorry for being delayed a little bit. So it's my pleasure to introduce Professor Barbu. Professor Barbu is a professor in statistics department at Florida State University. And Professor Barbu holds 2 PhD degrees, one in mathematics, another in computer science from UCLA. If you guys are familiar with MCMC, and you should know the superposition one algorithm, and after superposition one, there's a very famous improvement called superposition one cut, is developed by Professor Barbu. So right now, Professor Barbu is working on a whole range of machine learning problems, and today he will present us the online regression with model selection. So without further introducing, let's welcome our speaker.
Thank you, Tianfu. So this is work I did in the last about 2 years with my student Li Jue-sun. And so I'm going to talk a little bit about the literature in online learning, and I'm going to present our method for online learning with rounding averages, and we also have some theoretical guarantees for some versions of our methods. And I'm going to show some experiments and talk a little bit about conclusion and future work.
Actually just push on the arrows on the left there.
This?
No, the left. On the left there are arrows up and down
Mm-hmm.
to switch slides.
Okay. So why do we do online learning? So we do online learning because maybe we get so much data that we cannot just store it on the computer. And there are different kinds of online learning. You can think of online learning maybe when you have a lot of features, a lot of variables, and a lot of data. But this one is in the online learning setting where the variables are not that many, let's say at most like 20,000 variables. But you can have as much data as you want. And with online learning, the idea is you don't want to store the data, you want to update your model while the data is coming, and then you can do predictions based on your model. And we assume that the samples could be IID, or they could even be adversary. That's fine. Wow. Okay. So in the online learning, in general, we assume that we have some observations. Some observations that are coming, and in the online learning setting, you first predict on the observation, and then you get the label if you want to update your model. So you first do the prediction, then you get the label, and then based on your prediction, you get some value of the loss function. There is a loss function that you want to optimize. And then you update somehow your model based on the current parameters. These are the current parameters, let's say WI of your model. And the Z is X and Y. X and Y together form the Z. Yeah. And the target is to minimize this cumulative loss over the training examples. So to measure how good an online learning algorithm is in minimizing that cumulative loss, you can compute this regret, which is the difference between the cumulative loss and the minimum value of the offline loss that you could get if you had all the data. So that's called the regret. And you would like to make this regret small. And ideally, you would like it, because it's divided, you see, by 1 over n, you would like it to converge to 0 on the order of 1 over radical n. The most standard method for online learning is called stochastic gradient descent. When you have new data, you update the model based on the gradient of the loss, but only based on the new data that you have. And yeah, it's quite all. But the stochastic gradient descent doesn't select features, only updates these model parameters W. So we would like to do online learning and select the variables of interest, because maybe out of those tens of thousands of variables, only a few are relevant. And if you think about it, if you have a little bit of data, you can only discover this very strong features that are very strong in predicting the outcome. But if you have more and more data, then you can look at smaller and smaller, weaker and weaker variables, but which can still have a little bit of influence on the model. So ideally, you would like to adapt your model. Maybe at the beginning, if you don't have much data, maybe your model can only have like 10 variables, but maybe after you get millions of observations, you can afford to have a model with 1,000 variables, because you can detect weaker signal. And we're going to see in our methods how weak the signal it is based on the number of training samples. So there are some recent works that do online learning with feature selection, basically with sparsity. In 2009, Langford proposed a method based on truncated gradient, and Schwartz designed this stochastic mirror descent. But these methods, they all are based on having some coefficients and maybe truncating them at each iteration, but still you only maintain one set of coefficients. And that can be a problem if you, as I said, you want to increase the number of variables as you get more data, because you already decreased your sparsity to a certain level, and maybe it's hard to recover to another level. And there are some more recent works, online proximal gradient, regular dual averaging. So the mathematics is pretty nice, and the optimization looks nice, but actually these methods are quite slow in updating the model, and we, like in our experiments, these took days to run, and they don't recover the true signal with high probability. So if in our simulations we couldn't see the true variables, we only have like 1% or 2% of the true variables were detected. So SGD cannot select the true features, and these select features, but actually they cannot select the true features. So they don't have guarantees for feature recovery, true feature recovery. And in our framework, we're going to see that we have such guarantees. So the idea of this running averages framework that I'm going to present is that we don't want to directly commit to a model. We are going to update, based on the data, we're going to update some sufficient statistics, which we call running averages. And then from these sufficient statistics, we can get any of these models at any time. And even if you later on, you have these sufficient statistics, you will change your mind, you want to switch to a different model, you can always do that. And then from any of these models, you can get the coefficients. And at any time, you can change the degree of sparsity, because always this is not, you didn't commit to anything. This is always keeping all the information, sufficient statistics about the data. So again, we have training examples, xi, this is a vector, and the response yi. And we want to compute these. These are the running averages. So the Sx and Sy are just the means, the average of the x for each variable, the average of the y. And then here we have, this one is the biggest, x transpose x. Each of these xi transpose xi is a p by p matrix if these variables are p-dimensional. So here is the memory constraint of our method, that you need to memorize this matrix P by P. And then this is a vector and this is a constant. And how to update them, I show you here for mu x, but all of them are updated in a similar way. So the new mu x, if you have one more observation, is the old one multiplied by n over n minus 1, n plus 1, plus 1 over n plus 1 x plus 1. So that's one way to compute this in an online fashion. Okay, but if you want to do feature selection, you cannot just use this data. You want to standardize it. You want to subtract the mean and divide by the standard deviation so that the different variables, they have the same range, so that you can compare them and you can decide which ones you want to keep. Otherwise, just the fact that one variable has a larger range might influence in it being selected in your model. So for that, we need to do data standardization, and that can be done at any time from the running averages with this formula. So this is what we want to do. So we want to subtract the mean. We want to divide by the standard deviation. This D is a diagonal matrix with the inverse of the standard deviations. And for the Y, we also want to subtract the mean. And this, you can do some mathematics and figure out that all the running averages of this normalized x and y can be obtained from the running averages of the original x and y. For example, the SXY has this formula, D times SXY minus mu y d mu x. And this D is basically the inverse of standard deviation. That one can be computed from the running averages. And then for the SXX, we also have this formula. So basically, we have a way to normalize the data always from the running averages. And then we just say that we have this at any time. Okay, the normalized running averages. Okay, so here is what we can do with our model. We can do model selection. So at any time, we have our sufficient statistics, this mu xx, mu xy. We can get the regularization path. So this is the regularization path obtained with the online version of the lasso. So with any parameter, I'm going to talk about it in a little bit, but if you're familiar with the regularization path, it looks like this. So this is the penalty parameter which controls the degree of sparsity. If you have a small penalty like 0, you have all the coefficients like OLS. Then as you increase the penalty, more and more of them will become 0. And if it's very large, all of them are 0. So you can get this at any time from the running averages based on our model. And this is with another method which we call OLS with thresholding, which, so if you look at this, this imposes a bias in the coefficient. You see, these coefficients, they are very large, and maybe they should be like this because these are the two coefficients, but these other ones, they should be 0 because they are irrelevant. But as you increase the penalty, it makes those 0, but it makes these smaller. It biases them. That's the L1 penalty. Whereas this doesn't bias them. So you can have, like here, let's say you have only a few of them non-zero, and they have unbiased values. And actually they are bigger because these variables actually are correlated. And because they are correlated, the model, if you include irrelevant variables, will have these coefficients smaller than if they were not included. Okay, so that's what we can do with the running averages. So here are different versions of different algorithms using running averages. So online least squares. So to do least squares, we solve the normal equation, x transpose x beta equals x transpose y. And that one is just, in terms of running averages, sxx beta equals sxy. So we can do that in the online version. So then, to do feature selection, there is a very simple algorithm that you can do. And actually, people didn't pay much attention to this algorithm, but we dug theoretically into it, and we saw it has pretty nice feature recovery properties. So you can take the OLS, and that's in the setup where you have a lot of data. Like in online learning, you assume you have a lot of data. Usually the number of observations is larger than the number of features. So in this setup, you can do OLS, and then you would like to actually would like to solve this constrained optimization. So to minimize, like to fit the response as well as possible with your linear model, but with the constraint that only a small number of coefficients are non-zero. So that's what you would like to do, but actually this is a hard problem, non-convex, and we just obtain an approximate solution with the OLS thresholding. In OLS thresholding, we fit the model by OLS, which can be done online. Then we just keep the largest variables for whatever k we want, and we say that's our model. And then based on those k variables, we refit the model on the selected variables, because it's going to be different than the original model, because the variables usually they have correlation. Another method that we can make online is the feature selection with annealing, which we proposed in 2017. So this method iterates two steps. One is a gradient descent step, and the other one is a thresholding step, but which keeps a certain number of variables, but the number of variables that are kept is gradually decreased. So initially, you start with the model on all the variables. And then after you do one gradient descent step, then you have the coefficients. They know a little bit about the variables, and you can remove the smallest coefficients. So it's like it's like the Olympics. So in the Olympics, you don't do like in boosting. In boosting, what do you do in boosting? You say, this is the best variable, this is the second best. So it's like you have the whole of the world, and you say this guy is the best, directly without any competition. Now in the Olympics, you first have an initial trial where you eliminate really easy examples which are clearly not competitive. Then you have them compete, then you eliminate more, and then at the end you only have a few which you make them compete with each other to decide which are the best. So that's similar with what we do. Initially we have a model with all parameters, then at each iteration we remove the weakest ones, and whatever we remove, we never look back. And because of that, the algorithm becomes faster and faster, because the number of the model will be smaller and smaller. And then this method, if you compare it with boosting, for example, could be like 100 times faster than boosting. And it's like 1,000 times faster than L1 penalty. And it works very well, and we have theoretical guarantees for consistency. We proved theoretical guarantees for consistency and convergence. So here we present an online version of that. And the idea is that the gradient of this algorithm requires the gradient of the loss function. That's the loss function. The gradient can be updated based on the running averages. So here is the online feature selection with annealing. We start with the coefficients all 0. And at each iteration, we have a number of iterations like 500. We update the coefficients based on the gradient, just one step of gradient descent. Then we keep the m largest variables, where this m is, we call it an annealing schedule. Initially, the m is all the variables, and it gradually decreases to the number of variables that you want. And at the end, you've selected the variables. Then you refit by OLS to get the best model possible on those variables. And we can also do all kinds of penalized models, like online lasso, online MCP, online adaptive lasso. Online lasso has the square loss plus L1 penalty. And the lambda controls the degree of how much penalty, which imposes the sparsity.
Does this depend on the amount of memory that's in your process?
Like this method?
Yeah.
Yeah. So if
because as you're thinning your coefficients, you're forgetting things, right?
Yeah, but so you assume, so you mean for the FSA, for the feature selection with annealing?
Yeah, for instance, what you call the OLS with thresholding.
Uh-huh.
And you're basically doing it as you go, and you're thresholding each time you.
Yeah, so the most memory intensive is the SXX.
No, what I mean by memory, I mean in terms of correlation. The extent of correlation in your process. I mean the memory in the probabilistic sense, not in the actual physical memory.
So we assume that their IID, or yeah, maybe they could be correlated in principle, but yeah, we didn't study correlation between the observations. You're talking about correlation between the observations.
Yeah, I guess I'm basically just wondering. It's a very good idea, but it seems to me that it will depend on the underlying process that you're analyzing. Mm-hmm. In other words, there may be some processes for which, the tail of your correlation does not allow this thresholding to work very well.
It's possible, yeah. So we in our theoretical analysis, we assume the observations are IID, so there's no correlation between them. Okay, so we have the online lasso, and then actually in ZOL 2006, it was shown that this online lasso does not select the true variables. So it doesn't have true variable selection guarantees. And then they proposed this called adaptive lasso, in which each coefficient has its own weight. And the weight is basically just the OLS coefficient, like I think 1 over the OLS coefficients in absolute value. So, and then they proved that this one has the true feature selection property. And indeed, in our experiments, this works better than this. So this can be done in our framework with the running averages. So we have assume we have these running averages that are updated online. So we further compute the OLS, which can be done online. And then we compute this weighted matrix. Then we update the coefficient based on this weighted matrix. And here we use the self-thresholding operator. The self-thresholding operator subtracts a little bit from beta, and then whatever is close to 0 makes it 0.
How do you pick sigma W?
Sigma W is based on, is the OLS, absolute value of the coefficients, on the diagonal. So that's the adaptive lasso. If you just want the lasso, then you don't need this. You just directly. So sigma W is 1 for the lasso. Okay, and then another more recent work are these non-convex penalties, which don't bias the coefficients. So if the coefficient is large and it doesn't need to be killed, it's not going to be biased much. And the penalty looks something like this. So has more complicated term, but basically it looks like it has a spike at 0, and far away from 0 it's almost constant. And they proved that they can recover the support of the true features with high probability. And we can do that in the online framework. We need this thresholding operator. So this one also subtracts a little bit from from each variable, then divides by this. Then if this is if it's smaller than a threshold, actually if the t is less than a threshold is 0, then it has this value to bring it to b lambda, and then it's unchanged for large variables. And so the algorithm again updates the coefficients by the gradient, and then does the thresholding operator, and does these many iterations, and depending on the value of lambda, you get a certain sparsity level. So that's the issue with these penalized methods, that you control the sparsity indirectly. So if you say you want 1,000 coefficients, non-zero, you need to tune your lambda until you get 1,000. So you need to do it many times. Whereas in the online FSA or the OLS thresholding, you directly specify the sparsity level in terms of non-zero coefficients. So that's more direct and easier to use. Okay, so this was for regression. How about classification? In classification, so we cannot use other loss functions in this framework. You can use the square loss. But actually, we found a theoretical justification to use the square loss in classification. And so there is a theoretical justification saying that if you have a GLM, like a single index model, let's say like the logistic loss, then you can use OLS, and it's going to recover the true feature. OLS, no, not OLS. You can use lasso. So if you use lasso, you can recover the true features for these single index models with high probability. So that gives a theoretical justification, and then we can just use them directly as they were regression problems, and in practice they work pretty well. Okay, and then what is the computation and memory complexity? So for the memory complexity is O of p squared, because this SXX is p by p, so that's the biggest thing that we need to memorize. Then to maintain the running averages at each iteration, for each batch, for each observation, let's say, if you update all that matrix is p squared, so for n observations of np squared. So it's a little bit more expensive in terms of p, but you get, for that cost, you get the fact that you can always change your model at any time. And then the computation complexity to obtain the model is O of p squared. And if p is less than n, this is better than O of np, let's say, which means to go through all the data once. And for OLS and OLS thresholding is O of p cubed, because we need to invert the matrix. And then in online learning, there's another issue called model adaptation. What happens if the distribution underlying the model underlying the data is changing over time, like slowly drifting? What can you do? And we figured out a way. So the original update I'm showing here for the mu, all of them, they look the same, has like mu n plus 1 is mu n times this 1 minus alpha n plus alpha n times the new observation. So what does this mean? It means that the recent observations, there should be a parenthesis here, 1 over n plus 1. the recent observations, they have less weight than the original ones. Actually, no. Always, all the observations will have the same weight, if you think, because this is changing. So all the observations have the same weight. But in model adaptation, what you want is you want the older observations to have less weight, because the model is changing. So that can be done very simply to use larger alpha n. Instead of alpha n 1 over n plus 1, use 1 over square root of n, for example. Or, even more extreme, a constant. So that will mean that all the observations decrease at an exponential rate. And we experimented, so this is a classification experiment with some pricing. And the model, so these are the coefficients, and they change in time, like on a sine wave. Some become larger, some become smaller. And there are some of them which are 0. So it's like the model has like 1,000 variables, but only 10 are non-zero. And this is what the model without adaptation would do. So it would quickly go to some values and would stay there. And then using model adaptation with this alpha 0.01, you get this changing coefficient. And they follow the pattern quite closely. And this is very interesting here, that this variable sometimes is in the model, sometimes is not, depending on the data. So if there's not enough data, because this variable is the weakest up to a certain point. If there's not enough data, then it doesn't figure out exactly that it should be in the model. So sometimes it's in the model, sometimes it's not. But then after there's enough data, it's clear in the model and it stays there. And these are the MSE. This is with model adaptation, without model adaptation. And the MSE is 1 because this regression data has noise of standard deviation 1. So you cannot do a better MSE than 1. Okay, so we have some theoretical analysis for in 2 ways. One is we can prove pretty easily that the online versions of these algorithms are equivalent to the offline versions. So then we get for free the theoretical analysis for the different offline versions, like the lasso, adaptive lasso, MCP. We get all those for free. So that seems pretty easy to prove, that minimizing this loss function with any penalty is equivalent to minimizing this loss function, which is in terms of running averages. And here's the penalty. So this shows that the whatever minimizes this also minimizes this, and vice versa. So then this gives us theoretical guarantees for the MCP and lasso and adaptive lasso and so on. And then for OLS thresholding and for FSA, we have other guarantees. So for OLS thresholding, so we have the model. These are the true features. This is the data with some noise. IID, drawn from some normal with some correlation, multivariate normal. And let's say this is the support of the true features, and it has a sparsity of k star. And if the coefficient, the smallest true coefficient, is bigger than this quantity, which is log p over n. It only depends on the number, log of the number of variables and the sample size. Then for any, so and the penalty, if the penalty is, no, so this lambda is here. And basically what you need is that the x transpose x is non-degenerate, the true x transpose x. No, okay, so we have two versions. This one is with x transpose x, with the data that you see. But there is another version which has here the minimum eigenvalue of the true sigma. But that's a little bit more complicated, but it's very similar. Then with high probability, where these are some constants that we know, the index of the top true variables, so if you do OLS thresholding, let's say with the K star, are exactly the true support. So we can recover the support of the true features with high probability. This is with OLS thresholding. And what's interesting, so in many of these methods for feature selection, this true feature recovery, we have this bigger than some number times square root of k log p over n, usually. So there is a k here, where k, or k star is the true sparsity. And my student proved this without k star for OLS thresholding. So that means he can, like no matter what k star is, he can still select the true variables with the same probability. And I didn't believe him, and I told him to do an experiment. And he showed me this. So this for different data sets with different k stars, I mean, the y has to be based on different k stars. This is the variable detection rate for 2,000 oscillations and 3,000. And totally there are 1,000, p is 1,000. So what we see is that the variable detection rate increases. So it's kind of counterintuitive. But it's confirming this, that this doesn't depend on k star for the OLS thresholding. And then for FSA, we have a kind of similar result that, so if the coefficient, minimum coefficient of the true, minimum value of the true coefficients is bigger than some number times k star log p over n, then after these many iterations, the algorithm will find the support of the true variables with high probability. But this has some pretty strong constraints, basically on the correlation matrix of the data, which is based like these numbers. There's this like isometric, restricted isometric property, I think it's called. And basically the eigenvalues should, largest eigenvalue over smallest eigenvalue should be less than this number. So which means they're almost all 1. So that means the correlation matrix is almost diagonal. So under those constraints, we can recover the true feature with high probability.
So you do have an implicit, actually, an implicit k star in your formula.
Yeah.
If you go back, because you have the range of your lambda and you have sigma, right? So in a sense, that gives you kind of some notion of density of coefficients in that interval, does it not?
Yeah. So you assume that.
So there is an implicit. It's kind of an implicit k star, as you would get, for instance, from the minimum description length or something.
So the k star is only here. So in X, there is no k star. X is only based on this sigma.
But for instance, in the denoising problem, you know, the typical threshold that you would get is the MDL type of threshold, where you would have a dependency on both the model order, which is your k star, right, as well as the coding length, which is your log of p, right? Here you do not have the explicit
k star.
the explicit presence of your k star, but it's implicit. I think this is my opinion.
Yeah, but so you say it's about the lambda, but the lambda and the sigma, they are not involved in the K star. K star is only in the...
I'm saying your lambda is involved in your...
in your form, yeah, in the formula.
In your threshold. And
yeah.
In that sense, that sigma over lambda gives you some sort of density.
Yeah. Like it's actually it's maybe like signal to noise ratio kind of thing. Yeah. Yeah. That's true. But the K star is only here in the back.
I understand. Yeah.
Okay, so this is the theoretical justification, and also we looked at the regret for the OLS thresholding. And what we could prove is that with high probability, and for any alpha less than 1, we can prove that the regret is O of n to the alpha minus 1. So actually so basically we can get regret like O of 1 over square root of n. We can get even better than that. But what we saw in our experiments was that the regret is like O of 1 over n. So it's very good. But we couldn't get to 1 over n. We could get as close as you want, like alpha minus 1, where alpha is arbitrarily close to 0, but we couldn't prove exactly that. And then for classification, there is this paper of Nakov from 2016, which says that if you have a model like this, where with some variable depends, this is the prediction, so h of x beta plus epsilon, then this least squares lasso can recover the support of the true features correctly for discrete responses y. So this gives us at least guaranteed that if you do the online lasso for classification, you can recover the support of the true features. The model, we don't know, but at least the true features. Okay, so then we did some experiments with simulated data and with some real data. So for simulated data, we looked at this data with uniformly correlated predictors. And this can be obtained pretty easily like this. For each variable, you generate a hidden z, which is just normal, and then you get the predictor as this hidden kind of bias times some alpha plus uniform noise for each variable. Okay? And this hidden alpha introduces a correlation between the predictors, and any two variables are correlated with alpha over square over 1 over alpha square. And in our experiment, we took alpha equal 1. So that means any two variables have a correlation of 0.5. And that's, if you just had two of them, is not that big of a deal. But if you have 10,000, means any of those 10,000 can influence your true variables. So it makes it quite challenging. And then the y for regression is like this. And for classification, my student just took this and thresholded it to get the y. So that means the data is, even in classification, is not perfectly separable. And then the true coefficients are, every 10th coefficient is a true coefficient up to a certain k. And this beta is the signal strength value. And we can see how the signal strength influences the results. So here are the results for regression. So we look, so this is offline lasso. This is online adaptive lasso, online elastic net, online MCP, online FSA, OLS thresholding. Then we have SGD, which doesn't do feature selection, so we don't have any variable detection rates for feature selection. This SIHT stands for stochastic iterative hard thresholding. Then this SADMM is the stochastic alternating direction of multipliers. And so we have here different signals and different P's. Here P is 1,000, here P is 10,000. The K, so the number of true variables, here is 100, here is 1,000. Then here we have strong signal and weak signal. Actually strong, medium weak, and very weak. So let's look at the weak signal. So if n is not large, very large, or the lasso, offline lasso does a good job, but then as you increase the number of observations, then these methods, they start to work very well. And if you look at these, the stochastic iterative hard thresholding and SADMM, their variable detection rate stays at 10%, so they cannot recover the true features. You would expect the more data you have to recover more and more of the true features. But it doesn't happen in this method. In the lasso, it happens. But we couldn't do this because it took too long. I'll show you, it took more than a day. And so for stronger signal, then if you look, these methods can recover the true features better than the lasso. And you see the elastic net, which is like lasso, is about as good. Okay, and then even for P equals 10,000, we can do this, but with lasso, we can only do like 30,000 observations because then it's becoming too slow. And so this is the variable detection rate. This is the MSE. MSE, you want it to be close to 1. So it gets very close to 1 for large number of observations. Then here is the computation time. So this doesn't include, for the online method, doesn't include the time required to update the model. So that, in the paper, we have a separate column for that. I forgot to include it here. So if you look here, 300,000 observations with the lasso take 11,000 seconds. No, 1,100 seconds. So, and we did 100 runs, so that's why it's very slow. And if you look at this SADMM, it also takes such a long time. But these methods, OLS thresholding, online FSA, they're very fast, like 0.2 seconds. Then if you have 10,000 variables, this is 20 seconds, this is 26 seconds. So still very fast. And if you look, the time doesn't depend on the number of observations. It's about the same. Because the time to update the model, the running averages, takes more time with more observations. And here is the regret. So this is or in the original scale, this is in the log scale. So this in the log scale is better to look at. So these methods, online FSA, online MCP, online thresholding, OLS thresholding, they all look like straight lines, right? So that means they go at that rate, which is 1 over n to 0. And elastic net, it's pretty good, but not as good. So this is for strong signal, medium signal, and weak signal. For weak signal, it's very good. Online MCP and elastic net are very good. And then these are the other two methods. This is truncated SGD and SADMM. So the SADMM doesn't even show it wants to go to 0. And this TSGD is kind of going to 0, but much slower. And then here are some real data analysis experiments. These are regression, these are classification. For regression, we looked at the wiki phase. Wiki phase is a data set of images of celebrities, and we used the VGG16 classifier to extract features from those faces. So instead of using some trained thing for faces, we just used the VGG16, which is trained on ImageNet, which just gives some generic features. And we use those generic features to predict the age. Yeah, for this, we predicted the age of the person. And we got an R square of 0.5. So that's why we have 4,000 features, and there are 53,000 observations. And then this year prediction MSD is for different songs. You have a set of features, 90 features, and you want to predict what year was this song released based on those features. And we looked at two models, one a linear model, and then because we only have 90 features, we took all products of features to have a nonlinear model. So then this way we get 4,000 features. And OLS thresholding is very good. And indeed, it helps to have those nonlinear. It gets a little bit better R square. And online FSA is very close. This TSGD SLDMM R square of 0, not very good. And lasso, for this, it can be used, but for this, it's too much, like 400,000 times 4,000 cannot be handled by lasso. And then for wiki phase, again, OLS thresholding and online FSA are very good and much better than the other ones. Then for classification, we looked at these two datasets, GZ and Dexter. GZ has 7,000 observations with 5,000 features. Dexter has 600 observations with 20,000 features. And then here in these cases, online FSA works better than the OLS thresholding, and lasso works pretty well, and these other two don't work very well. And for each method, we tuned the parameters to get the best result. So in conclusion, I presented online versions of many of these feature selection, offline feature selection algorithms like lasso and MCP and FSA and OLS with thresholding. We showed some theoretical guarantees for some of them, and we showed that the equivalence between online and offline gives us theoretical guarantees for those who have for their online versions. And the advantages for these methods is that they can recover the support of the true signal with high probability, and they have good convergence rate in terms of coefficients and in terms of regret, and low computational complexity. But the disadvantage is that it grows quadratic with p, which means it can only handle up to, let's say, about 20,000, 30,000 features to fit in the memory of a regular computer. So if you have less than that, you can use these methods. So in the future, we want to look at missing data. So if you have missing data, I mean, for let's say you have the model, you have updated based on with these running averages, but now you have a new observation for which you want to predict, but you don't have all the variables. So then you can build a model on demand with this method based on the variables that are available and predict based on that the best you can. And my student is looking at stochastic feature selection with annealing, which is kind of in the old framework with updating the model and with a certain sparsity, but the sparsity decreases as like in the feature selection with annealing. And then we might want to look at online decision trees and online boosting at some point. So here are some references, and our paper is available on arXiv. And thank you very much for your attention. you have any questions?
Yeah. So thank you for the great talk. It's very comprehensive, very detailed. So thanks. My question is that you in one of your slides you had this diagram where you showed data stream and then calculation of the running averages, and then you had these arrows, right? So one arrow going to algorithm 1 or model 1, model 2, model 3. So from there I had a sort of this feeling that depending on the type of data and the running averages that have been created from them, there may be certain ways to predict like which algorithm is the best for my particular data, right? And even the title of your talk said that model selection, so I thought that maybe by selection what you meant is that given the process or given the plan from which my data is being generated, you may have some ways of telling me that whether lasso is the best or thresholding is the best or MCP is the best. Is there a way to do those kind of classifications, that which sparsification algorithm is best for my particular plant?
I think it's like an art maybe, but so you saw the experiments, so my experiments make me convinced that the lasso is not good unless you have just a little bit of data. If you have a little bit of data, it might be better than other methods. But if you have enough data, so if we go to the experiments, you see lasso, if you have weak signal and just a little bit of data, is good. It's better than the other method. Otherwise, it's not good. So yeah, maybe you can include that kind of stuff. So at the beginning, I'm going to use lasso, and then I can switch to other methods. But in general, model selection, at least in the statistics department, means select how many features you want to have in the model. Because yeah, you get a different model with different number of features. But that's also another way to select the model, like what you said.
Actually, I was about to ask about that, because when you are setting, basically in the feature selection problem, you are setting, okay, I have that many exact number of features. So if we say like we have roughly about 10% features, non-zero features, a probability approach, maybe less or other approaches will work reasonable.
So in general, there are two problems. One is feature selection, one is model selection. Model selection means, at least in statistics, means figuring out how many variables you want to have in the model. I don't know. So here we assumed we know how many. We know that this was generated with 100 variables. We said, let's get a model with 100 variables, see which one does best. But there is this model selection problem, which is usually done with like AIC, BIC, like kind of minimum description length criteria, which look at the criterion which has model accuracy and model complexity in it and gives you a number. And then you select based on that number the number of variables that make the best trade-off. So that's the model selection. But we didn't want to include in the numerical experiments this model selection part because it's like a confounding factor. You don't know, is this result good because I have a better, this model selection fits better for this algorithm, or is because of the algorithm. So we didn't include here, and actually we didn't include in the real data either, because here we said we're just gonna look at different sparsity levels and just figure out with this cross-validate, like random splits, which sparsity gives the best test accuracy. So we kind of bypass that problem here either. But in principle, you can have the model selection as another issue and select a variable based on this criterion or something, or cross-validation.
Other question?
So regarding the problem of p-square growth of complexity, if I understood it correctly, that's because you multiply by a matrix, a p by p matrix in each iteration, right? Is that
because we memorize the SXX,
exactly,
which is an approximation of the correlation matrix.
Yeah, but then Sx has an iterative, a recursive way to be calculated, right?
To be updated.
To be updated, right?
Yeah.
So can't you use this fact to reduce the complexity from p squared to p? Because basically S beta is repeated somehow and a new part is added to that. So can't you do a trick to reduce the complexity to linear with p?
I mean, we didn't figure out, but if you think about it, since you need, so if you just compute S beta, it's like you're stuck to a certain model. So then you don't get the benefits of different models. But if you think, oh, I'm going to have like 1,000 models, right? If I have 1,000 models, I kind of need all those coefficients which make a big matrix. So maybe if P is at 10,000, that's like 10 times less, but it's still quite a lot. So yeah. But maybe some correlations, let's say if they're really close to zero, maybe you could sparsify the data somehow. But I don't know how you would work with an approximate correlation matrix.
Can I ask one more question?
Yeah.
So again, so I'm just curious, and I mean, it's perfectly okay if there's not a good answer to it, like right away. Maybe it needs a little bit more thinking. So the different algorithms that you described, especially for the sparsification, right? So the thresholding algorithms, for example. So the general formulation was that I want to minimize some, ax minus b subject to the x having some sparse features, right? So what if I also add, and this x for your case probably was coming from some data or something like that, right? So what if I also have some constraints which gives me, some other constraints on x? Like for example, if I say that I know that xk plus 1 is equals to xk, for example, right? So can these algorithms handle dynamic constraints like those, or would it make it like very complicated or something?
So xk plus 1 means you just have a new observation, right?
Right, and I know that the observation is related to the previous one by some linear or nonlinear relationship, for example. So, I mean, the data is not blind. That's what I meant, essentially. So if I have some prior information about the type of data that I'm getting, and the data is coming from some evolution equation or something like that, can I incorporate those evolution as constraints and run lasso with thresholding and things like that?
Maybe.
Yeah, it's difficult.
At that.
I've seen some that you can obviously you can impose smoothness conditions, but that's one step back.
Thank you. So sorry about that, sir.
Yeah, that's okay. Okay, so yeah, so time's up. There's no question. We thank our speaker again.